All right, hi everyone. So now we are going to continue decision analysis with more focus on posterior probabilities and also Bayes rule to see how we can get updated information to make more decisions with more certain results. So imagine that before we make any decision, someone magically tells you exactly what's underground. So here the example of land that has oil, or the land might be dry at the ends. So let's assume that we have everything and there's no uncertainty, no risk, and you know with 100% accuracy whether the land has oil or is completely dry. So if we had this kind of information, for example, if the land has oil, we can see from this graph, as we discussed in the previous part, we would definitely drill as it earns $700K. So if the land is dry, however, we would never drill and we will go ahead with selling the land, which can it results in 90K dollar instead of just drilling, right? So the decision becomes really easy for us, and the only randomness here would be whether the land actually has oil or not. So which comes related to the probability of oil and dry itself. So now let's talk about how we can actually use that new information to improve our decisions. Before we run any tests like seismic survey here, we start with what we call prior probabilities that we use so far. So these are basically our best guess about the world based on the limited information that we have. So even in business is very common. So that what's the probability of a piece of land has oil that we discussed previously? That's kind of early estimates are that we have from the subjective results that comes from experience or expert opinion, which is kind of rough market data, right? So we don't have any exact information about that. However, business often invest in additional information as well as research or surveys to get better information. So that's where we can collect new data and we can update our estimates in more smarter and with more objective way instead of being subjective. So once we have that updated information, now we can use that new evidence or new values. That's what where we call posterior probabilities that we also discussed in previous chapters. But now we are going to use it in better applications to actually make decision in business. So now again, going back to previous example of go for work case, that's exactly what's happening in that case. So we started with rough probabilities about whether the land has oil, and then we run seismic tests that we are now going to discuss in the next slide, which can cost money. And based on the test results, we can update the probabilities. So the big question here would be, is that improved accuracy worth the cost of getting more information or not? Because we are paying money to get valuable information, and it's rarely fair to get it free. So now, we can just move back to the previous example, and you can imagine that you are executive at a small oil exploration, and you want to decide whether it's worth to drill a land or not, but you should collect more information before making this big decision because it can cost you, and you might just not get any oil at the end, and you might lose the money and everything. So that's where the seismic survey comes in here. It's like doing some kind of prediction. Um, However, for example, give an example of medical MRI that you'll do but for the ground here, you will get something to get the patterns, and it can tell you whether oil is likely or unlikely to be there. So it's a kind of business part now using the survey. So here in this example, we have information that that survey itself can cost $30,000. So now that's where we are going to ask ourselves, if we spend that money, will that information we gain can really improve our decision enough to be worth it or not? So let's review that possible findings from that survey. So it can be favorable results where oil is very likely, or it can be unfavorable results where oil is quite unlikely to be there. And we also have some information, given information, probability of finding, given that a state of nature, which is oil or dry. And we have that kind of information in that decision table based on a different state of nature, whether it's oil or dry. So let's review it together. So we have the probability of favorable finding given that the land has oil is 60%. And we also have the favorable finding probability given that the land is dry, which is 20%. So given the complement rule you learned in previous chapters, we can say, okay, so probability of unfavorable results given that the land has oil would be 1 minus 60%, which is 40%, and similarly for the second part. So now we can say that we understand how systemic survey works. But now we want to put everything together. So the survey can give one of the two findings that we mentioned, favorable and unfavorable, right? So the land can be also in in two sets, like oil and also dry. So there are four possible combinations, like oil and favorable results, oil and unfavorable results, and similarly for dry. Okay. So here, to understand how likely each combination is, we use the simple term which we call joint probabilities. So you've heard about this term in previous chapters, but now we are going to really use it in decision making. Isn't it interesting? So now we want to compare and see what is the joint probability of having oil and favorable results and similar for the rest. So why does it matter? Because when we update our beliefs using Bayes' rule, these are the numbers that we need. So we can think of them as a kind of building block for the final decision we will make at the end. So let's walk you through from the first part. Oil and favorable results. So we can start with the chance of oil, which is 25% here, multiply by the chance of survey, which says favorable if there is oil. And we have the number 60%. And this is the final answer. So you might think of that calculation as simple, like multiplying some decimals, but it's really doing something for every business. So we are quantifying uncertainty here. So now, so here, based on using that kind of joint probability, we can now connect real world with that noisy signals that we observe from the environment. So now we want to compute the probability of finding without saying whether the land is oil or dry. So why? So far we calculated joint probabilities for all possible four possible combinations, right? So oil unfavorable, oil unfavorable, and similar for dry. So now we can answer a much simpler question here, which is how often does the survey report favorable and how often does it report unfavorable? So you should notice something important here. We are no longer talking about oil vs dry. We're just talking about finding itself. So to get this, we are now introducing or using the total probability rule to get this calculation done. So there are two ways to get favorable probability. One of them is to actually add two pieces together, which is probability of finding and oil, or favorable and oil, plus dry and favorable. So we discussed in the previous slide using joint probability, remember? And similarly for unfavorable results, you can calculate, okay, the survey tells us and gives us the favorable reading 30% of the time overall, and also unfavorable results 70% of the time, regardless of the state of nature of the land. And here's a side note for the total probability rule, how we can really use the previous knowledge and learning to apply in this example. So we also have a good case here to just recall that total probabilities, here we can call the entire diagram as all possible situations. So the red area on the left here, we have oil. So is all scenarios where the land has oil, and the right hand side, the blue area on this part is the all scenarios where the land is dry. So these two events are mutually exclusive. There's no overlap. And the green circle is the middle, is the event we are now interested to calculate, which is a survey's finding. So now we can notice that this green part is actually in the middle. We can say that it overlaps both oil and dry, right? So that means that the survey finding can happen whether the land has oil or doesn't have oil. So the total chance of finding here can be easily calculated. How? By summation of the part of green circle that lies in that oil region, which we hashed by purple color, as well as the part of green circle that can also overlap with dry region that hashed by red color. So the summation would be the total probability that we calculated in this line here, right? So, all right, so we now calculated joint probability so far, which called how likely each combination of a state and finding was. And we also calculate how often each type of finding occurs overall using the total probability rule. Now we want to flip the question around here. Instead of asking how likely is the finding, like favorable, unfavorable, given the state of nature, now we ask, given the finding, favorable or unfavorable, how likely is in each state of nature? For example, we can say probability of oil given the savor is favorable. And similarly for the dry and for every single possible combination that we have. So that kind of survey doesn't tell us the truth with certainty for sure, but it significantly shifts the odds for us. So you can see how we now flip around the question, right? So it can help us. How does this new information change our decision? So that's why we also calculated the probability of finding in the previous slide to now easily plug these numbers to calculate the probability of the conditional probability using the new information. So we now have probability of oil and favorable results in denominator, which we calculated in the previous slide, divided by the probability of favorable results, which also calculated using total probability. So similarly, we have all these numbers for every single situation now. So now let's put everything together in one picture, this probability tree diagram. So you can think of this diagram as a kind of a roadmap that can show how we move from basic information like prior probabilities to different more refined probabilities that we need to make decision at the end. So at the very top, we can see that here's the whole steps, starting from prior probabilities and conditional ones, which are the given information, followed by calculation that we need, starting from joint probabilities, and finally the posterior probability, that is the updated information we have given the finding results. So we can see now the probability of oil and dry, which was the prior probability, our initial belief about whether the land has oil or not. And these are the rough estimates, right? So before collecting any data. And for every, each of those states, we now move to conditional probabilities here. And the accuracy of the systemic survey would be if the land is actually has oil, what's the chance the survey says favorable? So that's why we have the number here. And if the land is actually dry, So what does the survey tend to report for us? So we are now going to answer this part. So these kind of situation can give us the second level of the branch. So once we multiply along each path, we get joint probabilities. For example, let's start from the first branch. We have oil 25%, and we also have the possibility of favorable results given that the land has oil, which is the given information, and multiplying by these two numbers we calculated in previous slides is joint probabilities that we put on top of each branch here. So now these values tell us how often each specific combination occurs in the long term. But now we use those joint probabilities to calculate the overall probability of each finding that we also mentioned in the previous slides, right? So for example, probability of favorable results is going to be favorable results given that favorable results and dry, we had this number 15%, and favorable results and oil like 15%. Just simply, sum of them. And similarly, for the unfavorable results, we do the same analysis. So you select unfavorable results and dry, which is 60%, and the second branch, we also have 10%. So we're just repeating everything on the tree diagram. You can see why we calculate these steps to come up with the final decision. So now we can say that we use these joint probabilities to come up with overall probability of each finding, which was resulted in 30% favorable results in total and 70% unfavorable results in total. And finally, at the right part of each branch here, we calculate posterior probability as the last step here. Now, our updated beliefs after seeing the survey results, here is the answer. For example, if the survey says favorable, what is the chance of having oil? So you can see we calculated in previous slide, right? So the chance was equal to 50%, which means that from the probability of the oil jumps to 50% from 25% if the survey says favorable results. And similarly for unfavorable results, we also have the number, which means the chance of oil drops to this number from 25%, the original prior probabilities. So that's kind of, the overall picture, the bottom line here is that the arrows on this diagram can show exactly how we go from the left side to the right side, and what we start from the left side to the right side, what we need for making a smarter decision. And all of this flows directly, flows into evaluating whether the systemic survey is worth its cost or not. So that's where we can discuss in the next slide. So now here we're just summarizing the posterior probabilities. So there's no new information. So we just updated our beliefs, and we can say what is the probability of having oil given the favorable result and similar for the rest. We just summarize every information here. Now the business question is asking that should we drill after favorable results? Should we drill after unfavorable results? And what is the worth of having survey? Is it worthwhile to pay more money to get that survey done or not? So that's where we're going to focus. Now we are ready to look at the full decision tree diagram here for the problem. So this is a kind of big picture now. The final model that pulls together everything we calculated so far. So we can see now we have the systemic survey starting from the left-hand side. We have two decisions, do systemic survey or not having any survey. So without any survey, we have the simple case, either drilling or sell. So we put the square shape because this is a decision. And for drilling, we have two uncertainty, right? Like a state of nature. It can be oil or dry. So that's why we put circle node here, which called event node. And doing survey, it can be again two possibilities, unfavorable, unfavorable. And for every single survey, we have two decisions. It can be drill or sell. Again, you can just pay attention to the graph shape and how we come up with circle and as well as box or square shape, which ties back to the the shape of or the type of analysis that we are doing, either decision or event node. So similarly, we are doing the same for every single branch here. Now we take our decision tree one step further. So we add posterior probabilities and the payoffs at the end of each branch. So that can give us the complete picture we need to evaluate each possible strategy. So on the left-hand side, you can see that we list the probability of we already calculated before. So first of all, we put the cost for the systemic survey, and there's no cost for not having survey, obviously. And for survey, we have two possibilities, unfavorable and favorable results. So we have a chance of 70%. We put the number just in front of the event, as well as similar for favorable results. And we also have updated information on the left-hand side, probability of oil, given that we have favorable results is 50%, and similarly for rate of oil, given the unfavorable results, 14% almost. So we put all those information on top of each branch related to each condition. For example, oil given favorable results would be this part that we have 50%, and we also have the first box is like 14% given unfavorable results. You see that's where we put those probabilities in front of each event, right? So now these values now we put it on the right side of every single event that we have, and that's the probability that we will determine the expected payoff when we choose to go ahead with drill, or for example to go ahead with sell. So these are the updated information now we want to calculate the next calculations. So now here we can now remind ourselves how we get the payoff at the very end of each branch. So if we drill, for example, and there is oil, the cash flow here is gonna be 800 for selling the oil because we get oil at the end, and $100,000 for just drilling cost, and we also have minus $3,000 for systemic survey cost itself. So the net payoff will be 800 minus 100 minus 330, and gonna be 670. The final payoff that we will put at the end of each branch. So that's why you see that number, and similarly we have the updated payoff at the end of each branch. For example, here the second one we will have minus 100 as a drilling cost, and there is no oil, so there is nothing to sell, and minus 30, and at the end the net payoff will be minus 130, and similarly we'll do the same for the next parts. Okay. So the next part would be here. Now we can move on to the next kind of analysis. So let's assume we want to decide in the first decision box, which is part C. We want to see if we want to go ahead with drill or sell. So what do you think? So now we should calculate the net payoff, the expected payoff for drill here, given that we have two conditions, oil and dry, with updated information here, right? So that number on top of node F is something that we call expected payoff for drilling if we have unfavorable results. So how we should calculate that? So you should come up with calculating expected payoff given that updated information for probability of oil, which is 14%, multiplied by the whole payoff for this direction, plus probability of dry, which is 85%, multiplied by its payoff. So we have this calculation here. So for every single component, we just calculated the payoff, and then combination would be summation of these two components, resulting in minus 15.7. So which we can say easily that the expected payoff here is gonna be lower than the selling the land itself, because selling the land is gonna be 60 a net payoff. Why? Because we have 90K as a payoff or profit minus 30 cost of the survey. So it's gonna be 60. So still 60 wins compared to the minus 15.7, right? So that's why we should select sell option here. So we are doing the same analysis for the next decision box. Again, we should calculate expected payoff on top of each event node and compare it with the net payoff for the other alternative, which is selling. So we have 270 compared to 960 here. So pay attention to compare it with 60, not 90, because it's a net payoff at the end of each branch, given the survey cost as well. So we can say, okay, drill is the best option for me if the result is favorable. And similarly, we have it for no-seismic survey. Of course, this is the same case that we calculated earlier, which is the basic calculation of expected payoff using prior probabilities because we are not updating anything, okay? Because we are not doing any survey here. So that's a reference case. So what's the next part? So now so far we decided for every single decision of C, D, E, which decision I should go for. And it's shown here by check mark. So now the next part is, because we are going to answer whether we need to do a seismic survey or not, but here we know that for not having any survey, the result is going to be drilling and the payoff would be 100. However, for doing survey, we should come up with some number here. It's a kind of single value, which is 123 that is calculated based on these two directions, two alternatives or states. So which is telling that the probability of unfavorable result is 70% multiplied by the payoff, the maximum payoff, the best option, which is 60, if you sell the land, right? And if you go ahead with survey and it's unfavorable, so you should go ahead with the drill option, which can result in 270 net payoff, expected payoff, right? So now just do the simple expected payoff calculation based on this updated information. So we have calculation here on top. So 60 is gonna be the expected payoff for part C multiplied by the probability of unfavorable results plus 270, we have this number here, multiplied by the probability of the favorable results. So the answer would be 123, which is the expected payoff for doing the seismic survey. So now that's the time to compare these two decisions, do seismic survey or not having survey. So obviously we can say 123 has a higher value compared to 100, right? So let's select seismic survey and put the final value, maximum value on top here. So you see how it works. So we go ahead from backward calculation. First of all, calculate the payoff and also put in the expected value for every single event node to come up with single value and make better decision for part C, D, and E. And then finally go ahead with the final decision, which is making seismic survey or not. So how we can now simplify that kind of complicated analysis? So we know that seismic survey is right, but we can also come up with some policy recommendation, which is very worthwhile in business. So once we account for the value of information, that seismic survey is only useful when our prior belief about oil is in a kind of middle range. Why? Because if we know that the prior probability is very low, so there's nothing that we can for sure say 100% that there's oil at the end. So that's where we can say, okay, we should simply sell the land without doing any survey. But if the prior probability is very high, like something like above, let's say 30% or so, we can say the drill is so we have that kind of like oil results. So that's why there's no seismic survey, we should go for it. So if we have a higher like probability for oil. But if we have something in between, like the probability of something in the range, so that's where we should do the survey. And when we are doing survey, drill is favorable, and also sell is not favor sell is the option when the survey is not favorable. So you can see how we now summarize everything. So doing survey, if yes, okay. If favorable, which direction? Sell. We should go ahead with the drilling. And if unfavorable, which decision? Selling the land. And similar, if not having a survey, so we should directly go ahead with drill. So you can see how we now simplify our decision for policy recommendation at the end. So the optimal decision completely depends on how confident we are about the prior probabilities before collecting any new information in this case. So now about up until this point, we calculated mostly everything for the decision based on something that we can say people make decision purely based on that expected monetary values. But in real life, it's not true because people don't treat money in perfectly logical way, and we have some emotions. So that means that decisions are influenced by risk preferences. That's where from these slides we're now going to talk about this topic. So because people don't think about dollars, so they think in feeling. Why? So that's why we're using utility. So utility terms, it's kind of transforms money into personal value that capture risk aversion. So that's why someone might prefer, for example, 40K dollar over a gamble to get 50K dollar in expectation, while it has higher value, but because it has risk, so they might just avoid coming with that direction and just stick with the real certain value. So that's why utility is important here. And that graph shows also the typical utility function for the money that is mostly for risk averse person. And that horizontal line is related to money and the vertical is a utility. And you can see that, for example, going from zero to $10,000 gives us a big jump in utility. And when we just move on gradually to the end, going from, for example, 60,000 to 100,000, it raises utility a little bit compared to the previous ones, for example. So that's the kind of care that captures the psychological reality of the people, how they care the security of the value of the money more than the value itself at uncertain chance, even if it has a higher payoff. So now from these graphs, we can see the different personality of different people, how they treat money. So one of them is risk averse, can be risk seeking or risk neutral. So what does it mean? Here, for risk averse, each extra money or dollar is worth less than one before it. So it means that risk averse people prefer the safe option over the gamble with the same expected value even. But risk seeking is something that the extra dollar is worth more than the one before. So that's why we have a really high jump here at the end. So that's why they prefer gambles and they are attached to big potential wins compared to risk averse people. And the last one would be risk neutral, which is the for people who they value each dollar, every dollar equally. And so the risk neutral decision makers only care about expected monetary value, so nothing as a kind of risk or risk averse. So why does it matter? So utility kind of can reflect risk attitude in decision making. So risk averse is more about small gains that matter a lot, and that loss can hurt more for them. But risk seeking, they think they wanted to gain more, and those small gains doesn't matter for them. And for risk neutral, we can say only the dollar amount matter for them. So if we have two choices given the same utility, we can say that even if money is different, your overall satisfaction is the same in this case. So So yeah, so far we discussed about now decision analysis using survey and to see how we can update our information based on the current information if we want to pay more money to make decisions, what is the utility and why in business people don't rely on that expected value even only as a metric, and they care also about their feeling when it comes to making any decision. So that's where that utility can come into play to be evaluated other than just the money, average money itself.